Hello. In the last lecture, we discussed briefly about stress vector and stress tensor and the corresponding relation. So, now we use the applications of that, where based on which we derive the corresponding governing equations. Okay. So, let us see how to derive the corresponding relation. So, there are several approaches. The one which I am going to explain is a particular approach. But depending on the methodology and then books, different authors use different approaches. So, what we are doing is we are considering this kind of a volume element. Okay. So, it is a tetrahedron, you can see, with a specific property. So, what is the property? If you see, so the face, this particular one, okay, this point we are calling say P. Okay. So, I am referring the face ABC. So, the assumption is this is the large face, okay, ABC. Okay. So, now if you consider we have the corresponding unit vectors like this E1, E2 and E3. Okay. So, now let us consider the face PAC, this one. Okay. So, if you see PAC, the normal is, see, this is E2. So, therefore, the normal to PAC is minus E2, right. So, similarly, if you consider PBC, this one, okay. So, the normal is, you see, E1 this side. So, therefore, normal to the face PBC is naturally minus E1, because that is the other direction, right. So, similarly, this bottom one, that is PAB. So, normal is minus E3, because this is E3. So, normal to it is minus E3. Now, the face left, that is ABC. So, that is at arbitrary direction. So, the corresponding normal is n bar, okay, right, and the T bar denotes the stress which just now we have defined. Okay. So, now what we are trying to do is we are trying to consider this particular volume element and then try to balance the forces. Okay. So, general approach as I indicated. So, people consider parallelepiped and then tetrahedron. So, here we have considered tetrahedron and trying to balance the forces. So, the approach is very standard. What is the approach? We try to sum up the forces in a particular direction and then take the limit as the volume element is shrinking to a point. Okay. So, that is what we are doing. So, let us consider ith component of force on the fluid element. Okay. So, since T is the stress, ith component is the stress vector multiplied by the corresponding surface. Okay. Well, when we say ith component of the force on the fluid element, what we are, this is the larger face ABC. So, the total contribution, it is an approximate sense, the total contribution is coming from only this face, because this is dominating compared to the other three. Okay. Then ith component of stress exerted by the surrounding fluid on the face, which is normal to E1. So, what is the face which is a normal to E1? Okay. So, that is PBC. Okay. So, what will be the ith component? Ith component of the corresponding on this stress. Okay. This is PBC, it is having normal minus E1, that is what we have indicated earlier. So, this is the corresponding stress, and as you know, why this one is denoting the surface where you have the normal, and I denotes the ith component. Okay. Then area of the face which is normal to E1, that means we are talking about area of the face PBC. This is just by general geometry, normal times the corresponding surface area of this. Okay. So, once we have that, then ith component of force on the face which is normal to E1. So, this is the stress, this is the area. So, this will give you the total force. Stress along ith direction on a face having normal E1. This is area of that face, and hence the product will give you the force on that face. Okay. So, that is what we have obtained. Now, this must be equals to the force acting on that, that by virtue of the face ABC using stress vector, the ith component of the stress vector multiplied by the area. So, this is the force acting in terms of the stress vector, and in terms of the individual component we have obtained this. Now, we must balance. So, the total force exerted we are balancing. So, this is the total force. Okay. So, before balancing, this is the total force, we are summing it up. So, you must understand this is the stress vector and these are the stress tensor. Okay. So, this total force, when I said we are summing it up, okay, with E2, E3. Okay. So, that is what, because on a face having normal E1 and ith direction. Now, there are two more, face having normal E2 along ith direction, face having normal E3, but along ith direction. So, that will be also T2I, T3I. So, these are also included. So, therefore, total force along ith direction is this plus this. Okay. So, that is what we have obtained. Now, what is the if you consider any volume element, so you have a body force. Okay. So, as you can see, the body force is a density and a gravity and a volume element. So, total force balance we are doing. So, this is the total force on the element along ith direction. Then we have added the body force, that must be equal to the total external force, if at all there is some acceleration alpha I. Okay. So, once you have this is the total balance. As I indicated, what is the general technique of deriving? We assume that the volume is shrinking to a point. So, therefore, we take the limit delta S approaching 0. Okay. So, you might be surprised on this limit how we are getting this. Okay. Okay. What is this delta S? Delta S is the surface element. So, with respect to length scales, this is of order say L2, L square, and this is volume element, this is volume element. Okay. Why? Because the body force is acting on a volume. Okay. And also this is the actual force due to the fluid momentum. Okay. This is again volume, but stresses act on the surface, therefore, this is surface element. So, with respect to length scales, this term behaves like L cube, this term behaves like L cube, whereas this term behaves like L square. Okay. So, if this is approaching 0, so these two approach faster to 0, therefore, we get this equals to this, and this is very important law, that is Cauchy's law of stress. This relate the stress vector with the stress tensor. Okay. So, this is very useful relation which will be used time and again for deriving various balance laws. Okay. So, I hope you get the corresponding relation. So, one can expand for example, if you would like to write T1, it is simply J1 and J. So, now summation on Nj. So, you can expand like this, suppose T1 is nothing but Tj1 and J. So, now summation on J is going on. So, therefore, T11 and 1, T1 and 2, 3 1 and 3. Okay. So, similarly, other you can vary the corresponding index and obtain. Okay. Now, we classify depending on the roughness, so what is the reaction, and then classify the fluids accordingly. So, if you take a surface element where it is a rough surface, then if the normal is in this direction and let us say you have a fluid on top of it, so the corresponding reaction will be in an arbitrary direction. That is accordingly it is shown here. If this is n bar, the corresponding stress vector is in some arbitrary direction. Okay. So, why is this? Because the fluid is the surface is rough. So, correspondingly you expect this is a typically real fluid. That is because, so you have a surface and then fluid on top of it. So, if it is real fluid, so due to the viscous effects, so there is a transfer of the viscous effects from the boundary to the top. So, due to the surface roughness and then the reaction of the molecules with the surface roughness, you expect it is in arbitrary direction. But on the other hand, suppose it is a perfect fluid, that means very smooth, we expect the direction of the normal and the stress tensor both coincide. Okay. So, this is typically on a hypothetical situation, perfect fluid, so non viscous case. Okay. Okay. So, now let us discuss more about the stress tensor. So, this is our Cauchy law, but in perfect fluid the stress vector is always along the direction of normal. Just now we have seen perfect fluid. Okay. When the surface is smooth in a perfect fluid, that is what is happened. Then since stress vector is always along the direction of normal, you take the proportionality, okay, as minus p, where p is function of x, y, z considering 3 dimensions. Now, n bar can be resolved like this, okay, but t is the stress vector. So, that can also be resolved like this. So, the same thing in shorthand notation, okay, because t is nothing but t 1, t 2, t 3. So, therefore, from this we can introduce this shorthand notation. T I is t 1 is minus p n 1, t 2 is minus p n 2, t 3 is minus p n 3 and okay. So, from this if you expand t 1 in terms of stress tensor, this one, but t 1 component in terms of p is this. Similarly, t 2 we can expand and the corresponding component is this, t 3 can be expanded and the corresponding component is this. Okay. So, this must be satisfied identically, but as you can see right hand side you have only n 1, n 2, n 3. So, therefore, in order to have this identically satisfied, what we have is the corresponding off diagonal entries will be 0. Okay. So, when I not equal to j, so t I j is 0. Therefore, what we get is this. Okay. So, only the normal corresponding diagonal entries are equal and one can define p from this. So, p is nothing but the average of the diagonal entries. Okay. So, that is what we got. Okay. So, therefore, for a perfect fluid the corresponding stress tensor is T I j is minus p delta I j, okay, and p is defined as the hydrodynamic pressure. Okay. So, in perfect fluid corresponding stress tensor, if you consider, the off diagonal entries will be 0. That means, there is no shearing effects. Okay. So, that is an important remark. Now, let us move on to the linear momentum balance, which is most important governing law. So, what we do is we consider a fluid element and we are representing it by density rho 0 dV 0. So, then this is after convecting and this is the corresponding external gravity forces, okay, and this is a small surface element normal and the corresponding stress. So, now what is the first basic law that we have derived is conservation of mass. So, the next important principle is nothing but balancing linear momentum, which is nothing but Newton's second law. So, that is what we are doing by virtue of this element. So, what is it says, rate of change of momentum of the fluid, okay, element is equals to the external force on the element, linear momentum. So, with the index notation, momentum is nothing but mass into velocity. So, rho dV, that is mass over that element, and then this is velocity. So, we would like to consider rate of change. So, therefore, we have taken the material derivative, that is equals to the external forces acting, which are due to gravity, let us say, or it could be anything. G bar need not be gravity, you can have some electric field or etcetera, magnetic field, and surface forces. So, when you are balancing, what are the total forces? You have body forces, and then you have corresponding external forces, okay, and then surface forces. So, typically what contributes to the surface force? The stresses contribute to the surface force. So, that is what. So, this is the external force due to G, and these are the surface forces, but we have Cauchy's law of stress. So, we are using that. Ti is Tji. So, it is I have already introduced small Tij and capital Tij. Generally we misuse this, time and again we can misuse, okay, people use it, okay. You can consider both are the same. So, using Cauchy's law we get this, then we use divergence theorem to transfer the surface integral to volume integral. So, the notation here, this is the stress tensor, comma j means this is exactly nothing but the derivative. So, T j I by x j. So, this is the shorthand notation we use. Okay. So, this is the shorthand notation we are using, fine. So, now we brought all the quantities under the same volume element. Therefore, what we get is, so since we are in the material frame, we can take it inside. So, this happens for any arbitrary volume element. So, you make it equal to 0. So, rho dy by dt. Okay. So, for this you have to use the identity rho f bar identity, that is very helpful here. Okay. If you see the corollary where we have defined as a corollary of Reynolds transport theorem, we have considered f equals to rho f. Okay. So, you consider the corresponding quantity here rho f. So, that corollary we have used, and hence we get this, okay, and this is this term and this is this term. So, this is nothing but the corresponding linear momentum balance. Okay. So, this is very much important for us, because any fluid flow, first thing is we try to go for the corresponding linear momentum balance, and then try to proceed further. Okay. Fine. So, next is naturally angular momentum balance. Okay. This we will not discuss the complete derivation, I give an idea. Okay. So, let us consider a fluid element, and this is a surface element. So, any interior point, the position vector is denoted by r bar. Any point on the surface, the corresponding position vector is capital R bar. Okay. And again this is a normal, and this is the corresponding stress vector. So, now what is the angular momentum? Angular momentum is you have to take r bar cross mv. Okay. So, that is the angular momentum. So, now this is momentum, then moment of momentum, that is r bar cross the momentum. Then what is our conservation principle tells? Rate of change of moment of momentum equal to moment of the external forces. Okay. Please do not be confused. So, let me explain. Rate of change of momentum, okay, moment of momentum equals to moment of the external forces. Okay. So, you consider the momentum, then you consider the rate of change of this. This must be equals to moment of the external forces. That means, you take, let us say f bar is external force. So, you take the corresponding torque, okay, that is r bar cross. So, that is what we are doing. So, rate of change of the momentum, and since we are having external forces, that is g bar. So, we are taking, and why we are taking r bar which is on the interior? because this is the body force which acts on the entire fluid element. Therefore, we are considering this, whereas here we are taking capital R bar, which is nothing but the position vector corresponding to the surface. The reason is straightforward, because the stress vector this is acts on the surface. So, this is a surface force. Therefore, the corresponding moment should be taken with respect to the surface position vector, whereas this moment should be taken with respect to the any fluid interior. Okay. Now, similar arguments, only thing is a cross involved. So, therefore, we use divergence theorem here, but earlier we have used on this straightforward, but now we have a cross. So, one can use divergence theorem. Let us say you put these two into summation notation, then use divergence theorem. Okay. So, then this also put it in summation notation and then use the corollary that we have. Then if you bring it everything to volume element and balance, what you get is the stress tensor is symmetric. So, that is that is the net result we will be obtaining. Okay. So, this finer calculations can be done. So, I am leaving it as an exercise. Again, this is not very difficult, as I indicated, just put it everything in summation notation and do as before whatever we have done, you will be able to get it. Okay. Fine. So, now we are ready to define the two fundamental equations of fluid flow. First one is conservation of mass and the second one is linear momentum balance. Okay. So, the first one is as I indicated. So, this is a conservation of mass and this is the linear momentum balance, where u denotes the velocity, rho denotes density and T J I denotes the stress tensor. Okay. Okay. Now, at this stage if you see if you balance the number of equations and unknowns. So, what we have is, so I am just repeatedly writing this. So, this is one equation and then in vector form if you write, let us say this is rho g bar plus divergence of t. Okay. So, this is one equation and these are three equations, each has component form. Okay. But then how many unknowns we have? We have u 3 unknowns and then stress tensor. Okay. So, we have 9 of them, but if it is a symmetry, if you use symmetry, 6 of them. So, we have only 4 equations, that means there are more unknowns. Okay. Sorry, there are more unknowns, yes, than the equations. So, that means still there is a lack of information. Okay. So, still we have to reduce, right. So, then who will do this job? So, this is very hypothetical. This is Stokes hypothesis. So, Stokes has postulated that the stress tensor T I j can be decomposed as, this is the along the diagonal entries and then something called strain tensor. Then what is the structure of this strain tensor? So, that is a question. Okay. So, to start with, the structure is, it should depend on the, see, stress tensor is resolved into principal, that is along the diagonal. So, then the off diagonal. So, these are nothing but they indicate the deformation. Okay. So, correspondingly some structure is put in. Okay. So, what is that? Each sigma I j should be a linear function of the velocity gradient. Okay. So, that is the shearing, linear function of the shearing, and each sigma I j should vanish if the flow involves no deformation. Okay. If there is no deformation, then this 0, and the relation between sigma I j and velocity gradient should be isotropic. That means we are not attaching any directional dependency. Okay. So, the isotropy is so this is the initial hypothesis by Stokes. So, then what happens? it appeared that the number of unknowns are reduced, but still these are still unknowns, and these are off diagonal entries. Okay. So, in place of 3 diagonal entries, we got 1 unknown, that means a reduction of 2 unknowns, but still we have off diagonal entries, right. So, still if you balance, the number of unknowns will be more. Okay. So, now what is the corresponding remedy? Okay. So, again it is proposed a constitutive relation, this is popularly known as constitutive relation. What is that? The corresponding strain tensor sigma ij is related to the velocities as follows. Okay. So, this is a first coefficient of viscosity, typically we call it dynamic coefficient of viscosity, and this is the second coefficient of viscosity. Okay. So, this is hypothesis, okay, and this is for compressible, and if it is incompressible, you can see this is nothing but dou u I by dou x I kind of, because this is dou u L by dou x L. So, it is a dummy index, this is nothing but divergence of u 0. If it is incompressible, we have divergence of u 0. So, this goes to 0. So, if it is incompressible, we have this correspondingly, as I already mentioned, this goes to 0. So, therefore, sigma ij reduces to this. Okay. So, once we have this, what will be the corresponding stress T bar is minus P I plus mu. So, I am just writing some notation which is not there on the slides. Okay. So, this is nothing but dou u I by dou x j, this is dou u x j by dou x I. Okay. So, this is exactly we get it, that is what we have. This is the corresponding strain part, and you have a normal part P. So, that is what exactly I have written here. Okay. Right. So, now with this, if you balance the equations, you will see the number of equations and the number of unknowns will be matching. How? You have velocity vector 3 components. So, therefore, 3 velocity equations, okay, and then you have one conservation of mass, that is one equation, 4 equations, and how many unknowns? Pressure and 3 components of velocity, you have 4 unknowns. So, the system is closed. Okay. Now, there are some limiting cases, as I already indicated, if it is incompressible. Okay. So, we have a general case, and then if it is incompressible limiting, this is the what already I have explained, summation notation, the corresponding vector form just now I have written. Okay. So, if somebody is interested in writing explicitly, you can see P contributes to only the diagonal entries. So, as you can see, T11 contains P, whereas T12 and T21 do not contain P. Similarly, if somebody writes T22, you will get definitely P and then the corresponding strain. Okay. So, this indicates the strain. So, for example, du1 by dou x2 indicates the strain deformation. Okay. So, that is a limiting case. Okay. So, this is the mean pressure. Then in the corresponding equation, we take the divergence and then substitute the incompressible stress tensor, okay, and this is the body force, and little bit of algebra one can very easily verify. It is very straightforward. We have not done any magic, simple operation of this into each of them. Whenever x j is equals to x j, we get a double derivative with a repeated index. So, that is x j square, whereas here there is a difference of index. So, that is this term, okay. But this is commutative. So, you bring it inside, and dou x u j by dou x j is nothing but the incompressibility condition. This is divergence of u 0. So, therefore, this vanishes, and what we get is the corresponding Navier-Stokes equation for incompressible. Typically, this is used. So, the same in vector form, this is equals minus grad p plus mu del square u plus rho g, and this conservation of mass. Okay. So, this is a typical incompressible Navier-Stokes equation. So, probably we have given. Okay. Let me compressible case this one. So, incompressible this is 0. So, that is what just now I have written. Okay. So, these are just to give you some idea about various limiting cases. Okay. So, that is not a big deal. Once you get the complete equations, you can always get the limiting cases. Okay. So, then what is the other limiting case? There will be competition across the forces. So, what are the forces available? So, you have left hand side, you have the corresponding convective derivative, okay, and then right hand side you have the pressure forces, then viscous forces and body forces. Okay. If you see the convective derivative, so some of the forces are, if you expand this, what you will have is the local derivative plus the convective derivative. Okay. Right. Now, if you assume that the viscous forces are neglected, then you get this. If the viscous forces are neglected, this is inviscid flow, and these equations are called Euler's equation. You can see there is no viscous forces, okay, in this. Similarly, if you neglect inertial forces under the assumption that viscous forces dominate inertial forces, then you get a linear equation. This is unsteady Stokes equation. Okay. So, these are some limiting cases. Of course, we will pay much closer attention to the competition between viscous and inertial forces when we discuss about the non-dimensionalization. Okay. So, otherwise once you have the Navier-Stokes equation, one can obtain various limiting cases. Suppose first case we have considered is, we have considered that viscous forces are neglected. Second case we have considered that inertial forces are neglected and get the corresponding limiting cases. So, with this I hope you get an idea about the role of stress tensor and then how that is useful in deriving the corresponding linear momentum balance. Thank you.